Hi, welcome back. Is it welcome back? Hi, welcome to Calculus. I am out at a friend's wedding, uh, but here we are. We're graphing derivatives. I kind of ended last class off in a bit of a rush because I just wanted to introduce you to this concept, so it's not super foreign as I'm not here and you practice this more. So we're practicing going a step further with graphing derivatives. And let me actually check first. Do we have a long class tomorrow? Long class today? No, it's a short class. So we're just gonna probably tackle this, maybe do some more practice with limit definition. But we're gonna work on how to graph derivatives. So last class we went over a couple of graphs. Let me see this. Where if we're given a function, let's say a function f of x equals x squared, and it wants to graph the derivative. So this is f of x. If I were to ask you to graph the derivative, how would we do it? Well, the derivative, that's way too thin. And I'm not feeling that. So the derivative is pretty much a slope. It is the rate of change at an exact point. So we want to see like how much are we changing? What is the slope at this point? So instead of x and y, we want to find x and the derivative, the change in y or the change in x. Derivative is slope. It has an informal definition, but this is how I want us to like understand it for now. We'll go more into like what derivative actually is. For now, we're just looking at it just as slope. It's how we change something. So let's look at the slope on this graph. And we always go from left to right. So always look this way. So over here, I see I'm decreasing. My slope is negative. So it's negative, it's still negative, it's still negative, it's still negative. I'm always decreasing on the left. Over here, it's not increasing, it's not decreasing, it's constant. So the slope is 0. And now over here, it's positive, 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 positive. So we see my derivative graph. I want negatives up until 0, and it hits 0. I want positives after that. So my derivative graph, I'll just make it negative. We could do any we want. Make it negative and go hit 0 and make it positive. We'll get into an actual shape that I want, but this has enough information for now. We'll refine it in a bit, but we see that I just want to be negative, I want to be 0, then I be positive. We want to line up. Exactly how we line up with that varies, but this is a valid answer for now. I will ask you to be more specific later. This is actually the correct answer, where it's negative, 0, then positive. You can make it like that, a bit less steep, but as long as you have it negative, 0, positive, we're heading the gist of it. So let's now formalize some rules, and it'll actually show us a graphic that might be very helpful. So let me get this graphic out from Calc Workshop. And let's take a look at this graph, this diagram. So here we see, with the graph of f of x up top and the graph of the derivative down below, we want them to line up. So at 0, it's 0. It's an x-intercept. It's negative to the left of that, and it's positive to the right of that. So we have it negative and positive. a bit more advanced. Over here, we have a lot of curves. But I'm negative, I'm positive, I'm increasing, and I stop here, I hit 0. Then I'm negative. We'll ignore the red one for now, but we see I'm negative, I go negative until I hit 0 again. And now I increase again, so I'm positive. So I'm positive, I'm negative, then I'm positive. Here, I'm negative, I hit flat. Now I'm positive, I hit a flat. I'm negative, flat, positive. So decrease, increase, decrease, increase. Whenever we switch from decreasing to increasing, or increasing to decreasing, we must get to a point, as long as it's continuous. Like, if it's not a vertical asymptote, if there's not a hole, if there's not a jump, as long as it is continuous, it must pass through 0. And this kind of ties back in intermediate value theorem, where if a function is continuous across an interval, it must hit every y value in between those intervals. So if I'm going from negative to positive, and it's continuous change, my slope is changing gradually, that's continuous, that means that to go from negative to positive, I must touch 0. To go from positive to negative, any positive value to any negative value, I must touch 0. So that's why we learned intermediate value theorem. It's just giving us proof for stuff like this. Now, as we do these graphs, some style things that I think might help us understand it more is that unless we see like abrupt changes, like, oh, that didn't work. Why is it doing that? Oh, that's new to me. But let's do like angles like that. A lot of times, I want our graphs to be kind of smooth. So we don't really want a graph up here, like something like this. That's kind of crazy. But we want like smooth lines, smooth curves, straight lines, but no real sharp angles. Like these, we'll learn exactly why and like why that is the case. But we see that we have gradual changes. So we're gradually getting to 0, then we're getting more negative, then we're going back positive. So it's gradual. So I'm going to give us, let's now look at these and develop some rule set. So to graph, we went over this last time, just reinforcing to make sure you have it. So if f of x is increasing, that tells me f prime of x is greater than 0. If f of x is decreasing, f prime of x is less than 0. And if f of x is at an extrema. And what are extremas? I'm saying this like you could hear your answer, but like extremas are mins or max. Min slash max. At min and maximums, unless they're absolute. This might come back to bite me, but I think this is robust. The derivative equals 0. So here is a maximum, we want to hit 0. A minimum, we hit 0. As long as we like are changing. So this goes to infinity, so we don't have any maximum or minimum there, but we set it. Min, max, min, 0, 0, 0. These are rules are where we're going to start off with to do some questions. So let's now try this. I'll probably have a worksheet given out with some graphs. And let me pause for a bit. Okay, so you'll probably have a worksheet with some questions where we would like you to graph on top of the same existing graph, on top of the given graph f of x. I'm going to graph f prime of x, the derivative. So here's an example. This might be one of the ones that you have on it. I'm going to make the worksheet the next day, but like you'll have it by now. Let's say we have this graph of it goes up, it goes down, it goes up, and it goes down. On the same graph, we just want to follow the same procedure that we had above, where wherever it changes, we want to add a little indicator. So see over here, that's where it's changing. Over here, that's where it's changing. Over here, that's where it's changing. So point it down. And these are my three x-intercepts. X-intercept, x-intercept, x-intercept. And also label if it's increasing or decreasing. So here it's increasing, then it's decreasing, increasing, then decreasing. So it should be positive over here, negative over here, positive, then negative. And we just want smooth curves. Oh, it's hard for me to draw. And this is my graph. So let's actually look at our derivative graph a bit more. Looking at this graph, we see that the directions tells us to do a bit more than what we have. And we'll see on the next page, you'll see some derivative graphs given to you, and we have to identify the existing function. I give you f prime of x, you must explain some stuff about f of x. So my derivative graph, I see I'm positive over here, then I go negative. If my slope is going from positive to negative, that means I'm increasing, I stop increasing, and I start decreasing. So I increase, I stop increasing, and I decrease. So if my f prime of x goes from positive to negative, that means that this is a local max, because I'm increasing then decreasing. If my derivative is the other way, from negative to positive, that means I'm decreasing and I'm increasing. So you go from negative to positive. This is a local min. Increase to decrease, positive to negative, negative to positive. A local min. So now, as you work through this works mainly with smooth curves. With smooth curves, we're able to graph it. But we'll see on our worksheet, there are some curveballs. Some curveballs that we have. And I'm going to point it out because I want you to think more about it. I'm not going to give you the answer just yet. We'll talk about the answers once we get back. But what if I have a graph that goes up, pauses for a bit. I'll make it flat first. That's flat enough. What if it goes up, pauses for a bit, then goes up again, pauses for a bit, it goes up. I'm still flat in some areas, but I'm not increasing then decreasing or decreasing increasing. I'm increasing then increasing. What might this look like, the derivative function? Another thing as well is keep track of what we learned. And also feel free to also estimate what the function would be and see what the derivative would look like. Because if I have a function like this, a straight line, it's always decreasing. But what might this try to be a bit more accurate rather than just making it negative the whole time? What else do we know about this derivative? And on the final curveball, actually, there might be some other curveballs. One other curveballs that you might have is absolute value functions. What if I go here, I have a point, then I go up. It's not a smooth curve, so it won't be a smooth change. So going based off what we did over here for the previous example, we know what this slope is. We know what this derivative is, what it looks like. Use that, because our derivative slope, our derivative line doesn't have to be continuous. We could have jumps in it. We could have gaps. We could have discontinuities in our derivative curve. But if this is my function, if you can find your absolute value example, think about what my derivative function will look like. So those are some curveballs. You might some have some other ones. So the square root function. You might also have rationals. But I just wanted to think about, what does the slope look like? How strong or how weak is the slope? And please use this, continue working, and discuss one other, try your best. And I'll say refrain from looking up for now. You can look up, I can't really stop you from looking things up, but I would encourage you greatly to try to work through this, talk to each other, work through this, and like struggle through this before, if you feel like you need to look things up. But also write down questions, because I will be back and I'd rather hear your questions and like see how you digested and learned this topic. Some other things as well is we went over limit derivative the last couple of classes, but I will emphasize a bit more because I feel like we still need to practice it. So if we are continuously getting it wrong, I'm going to do one example right here that might be helpful. So let's find that if f of x, actually also if you already noticed, some other logistics things is that I did post a survey on Canvas, and there is also homework. The homework, which you're doing now, like the worksheet with other stuff, the homework's like part of this worksheet. That's due as well as this. So like you can do this. You probably can finish most of, if not all of it, during class today. But that'll be homework for next class. So there's a survey online on Canvas, as well as the worksheet that you have right now. The worksheet will have some graphing stuff, identifying the derivative and working on it, as well as some limit definition stuff. We still have more stuff to do with this, so we're gonna not forget about this, dive more into it. So now here's a little example. So f of x is equal to negative 3x squared plus 2x minus 1. There's a lot going on here. One thing we know now is on the future assessment, you'll be asked to do more of this. That's why we're doing it again, with some other like harder variations, but you will learn some rules. We already know how to find f prime of x, and this would give me negative 6x plus 2. But writing this as your answer would give you maybe like, if there's a 5-point question, you get 1 out of 5 points. Because the purpose of this class is not, can you do calculus? It's not like calculus is an essential life skill. It's more like, can you digest and understand a more complex process? Can you do problems with these complex processes and be flexible with applying them? So that's why we're doing these topics. So you can use this, but to check your answer. Because we know our answer should be negative 6x plus 2. Just look back and like make sure our answer is negative 6x plus 2. Let's prove it using the limit definition. So limit definition is limit h approaches 0 of f of x plus h minus f of x over h. So this means I want to find a limit as h approaches 0 And this first piece right here, first term, means that I want to rewrite the function, but instead of using x, I want to write x plus h. So limit h approaches 0 of, I rewrite this, but with x plus h, negative 3 x plus h. When we plug something in, right parentheses, plus 2 x plus h minus 1, minus the function, negative 3x squared plus 2x minus 1, all over h. Now we simplify what we have. So I still write limit h approaches 0 of negative 3 times x squared plus 2xh plus h squared. Because I FOILed it, I did this first. Now I want to distribute here. 2x plus 2h minus 1. I want to distribute this negative, so plus 3x squared minus 2x plus 1, all over h. I still have to distribute this 3, the negative 3. So limit h approaches 0. At this point, this could go away. Negative 3x squared minus 6xh minus 3h squared plus 2x plus 2h minus 1 plus 3x squared minus 2x plus 1, all over h. Now, a little rule I told us before is that everything without an h must go. Because with this limit, I can't do it because h, if I put 0 for h, I'm divided by 0. And to get rid of it, there's no radical to rationalize. There's no infinite thing I could like use to make a table because like there's too much to do. I wouldn't ask you to do that. What we can do is factor. And you'll always be able to factor out this h. In order to factor it out, I must have h's on the top. So the first term, negative 3x squared, there's no h, so it must cancel out. And this cancels out. Let's use bright red. This cancels out over here. Those cancel out. This term has an h, so it might stay. And we see that there's no other term with an xh. That's fine. This one has h squared, that stays. 2x, that must go away because there's no h. And we have negative 2x. 2h minus 1 and plus 1, get rid of each other. So we're left with limit of h approaches 0 of negative 6xh minus 3h squared plus 2h over h. I saw one person do this on the test, which was a very good way of visualizing it, is instead of dividing it right here, right away, since I'm saying we could factor it out, let's actually factor it out. I factor out h, get negative 6x minus 3h plus 2. The h's cancel out. Limit h approaches 0, negative 6x minus 3h plus 2. Now we could plug in 0 for h. And once you plug in for a limit, the limit disappears. So negative 6x minus 3, 0 plus 2. Writing limit again would be incorrect. So this gets rid of each other, negative 6x plus 2. That is my third derivative, which is exactly what I had over here. So please review this, check over it. This is a skill we must learn before, because it'll be helpful for retakes, but also helpful for this upcoming assessment. It'll be helpful for the midterm. It'll be helpful many, many times. Okay, so please work, please do the survey, and please write down any questions you have. And I'll see you guys, I don't know, Wednesday? Maybe. Bye-bye.